Good afternoon, everybody, or whatever time it is that you're watching this, because that is one of the distinct advantages of this digital delivery system through which I'm teaching topics of Calculus BC. In this video, as you can probably see by the title, we're going to be talking about something called alternating series, which will include, of course, another test, in this case called the alternating series test. Big surprise, right? Having said that, unlike previous lessons, this one's not going to feature two convergence tests kind of mixed into one lesson. This is going to just focus on alternating series. And the reason for that is that the topic of alternating series actually opens up a bunch of interesting possibilities. For one, for many alternating series, well, if a geometric series is alternating, which we'll talk about what that means in just a bit, you can find it some using geometric means. But we're going to actually be able to find a way to get a really good bound or a good sense of how big the sum of an alternating series is. We'll be able to approximate it, and we'll talk about bounds later on in the course as well. And in addition, we'll also be able to talk about some other properties that certain alternating series have, such as they're called they're called absolutely and conditionally convergent. So we will get to address a bunch of other things. Basically, this topic's just a little richer. There's a little more going on than there is in the traditional topic, and for that reason, we have to take a little bit more time for it. So alternating series test is actually probably the smallest, most narrow portion of this lesson, this topic. Everything else kind of will feel like it dwarfs it by the end. But we will get you a new test just the same. Having said that, with all these videos, I've always started by kind of updating things. As of this moment, or the moment of this recording, I'm reading, or just reading, that I think the state of New York has kind of closed things down the same way we have. Supposedly Illinois is coming close. Maybe there's this tomorrow. So obviously more uncertain times ahead. But the one thing I've been certain of this whole time is that the times are pretty uncertain. So having said that, like, my big accomplishment for the day was I washed all my mattress bed stuff. So I cleaned all that stuff up. I watched a movie that I've had for a long time and I just never felt like watching. It was just okay. It wasn't even that great. And then I finally just settled on picking something out of the entire Netflix catalog to start. And now I'm halfway done with the thing. So there's good news and bad news with that regard, because now that I'm sort of invested in the show, it's going to end really fast. But yeah, I just kind of wanted to be able to get through something here and to start something, because otherwise I spend the whole time looking at the catalog and never selecting anything. So pick something and watching something that Paul read. So it goes. As far as things that are easier to handle and simpler than navigating the Netflix catalog and choosing what's next to watch, I'm going to talk about alternating series. And typically, when I taught this alternating series lesson in previous years, I kind of made a mistake. Well, not last year. Last year I fixed it. But in previous years, I made a mistake of just jumping in and immediately talking about the alternating series test, which will tell us whether or not an alternating series converges or diverges. The problem is, people didn't have a good command or grasp of what it meant to be alternating. Like, alternating means switching back and forth, but it's not clear what we mean by alternating in a mathematical way. So to start with, this might seem very small, but just to kind of illustrate, alternating is something that happens with a particular factor included. Like for us, there are lots of ways to generate things, but alternating typically is written in one of two ways. So the first possibility is that alternating occurs with -1 to the n. So basically what this causes is, if you have a factor of -1 to the n in your series, then you'll have the even terms as positive, or your even terms will be positive and your odd terms will be negative. So that is one possibility for an alternating series, or for something to be alternating, is if all the even terms are positive and all the odd terms are negative. On the other hand, if you have -1 to the n plus 1, or consequently n plus an odd number or minus an odd number, then instead you'll have the even terms be negative and the odd terms will be positive. You can see this is one of those situations where it takes a lot longer to write than it does to actually talk about. Apologies all. But there we go. So now, having said that, basically this thing that we're talking about here, this -1 to the n thing, which coincidentally, by the way, is also the same thing, if memory serves, as the cosine of pi n. Let me see if that makes sense. Cosine of pi is -1. Yeah, that's true. So this is the same thing. So, and this would be for n greater than or equal to 1. This thing that we're talking about, particularly this guy, either -1 to the n or -1 to the n plus 1, That thing we're going to call, using a name that I learned at the AP reading a couple years ago, we're going to call it the toggle. Toggle is just kind of a really simple name. It's a factor that's going to change the sign of all the individual terms. And the reason I bring this up is that, of course, we want to be able to tell if a series is alternating. Not that it has some terms that are positive and some terms that are negative, but that it meets this formal requirement, that it actually has that toggle changing the sign every other term. So basically, as an example, again, trying to be as thorough as possible here, I'm writing out a series. In fact, you might be able to figure out the pattern on this series. The question would be, of course, is this alternating or not? And the answer would be to check the sign patterns. I see positive, negative, positive, negative, positive, negative. That is firmly toggling back and forth between positive and negative. That makes this an alternating series. So alternating is when we have the sign change every single time. On the flip side, if we go something like this, you might think, oh, that's different. It didn't start positive. But notice it goes minus, plus, minus, plus, minus, plus. That would also be alternating. So basically, it doesn't matter where you start. It just matters that you change every single term. Every other term has a different sign. I think I said that correctly. Or consecutive terms always have different signs. I think that's a good way to say it. Now, having said both of those, just as kind of a reminder, if you have one, oops, sorry, this should have been 64. So if this was the series that you were looking at, and this is a series, by the way, that you could almost consider a challenge to try to determine a formula for. But if you look at this series, this one is not alternating. And the reason is, look at our signs. We go positive, positive, negative, negative. That's just not good enough. That's a different pattern. Yeah, we'll be able to analyze that pattern a little bit by the end of the lesson and talk about that idea of something called absolute convergence. But having said that, that's not an alternating series. So unfortunately, we have to be really careful to make sure it's there. So having said that, I just wanted to make sure we establish some of this vocabulary, particularly things like toggle that I'm going to mention a bunch, and also so that you have some context when you see all these alternating series today and see those -1 factors sitting there, that you understand where they're coming from. They're just there to switch the signs. And so basically this lesson, this topic, alternating series, is the first one we're going to look at that extensively has a bunch of negative terms, like where the signs are going to matter. A lot of what we've done in the past few days has included positive terms. So having said that, let's dig into the rich topic of alternating series. So first of all, I've rewritten it in the best handwriting I can possibly muster. Turns out having a bunch of time to do this, with little else going on inside the house, allows me to write really, really nicely and really, really large to honor either Lonzo Vision, if you're in my AB class at any point and you're watching this, or just to honor Brittany's demands and hope for good vision. So in this case, the alternating series test is much like the others. It offers some information about a particular type of series, it gives you some conditions that must be met, and then it says something about its convergence. So what it says here is that we first have to let a sub n be greater than 0. Now I know when you see that for the first time, your mind's going to start to go, hey, wait a second, I thought you were talking about all the signs changing. Well, keep in mind, the reason that we make sure and require that this a sub n term is always positive is that we want to explicitly include the toggles in our definition of an alternating series, or in our definition for the alternating series test. That way there's no muddying the waters between a negative sign that comes from a term and a negative sign that comes from a toggle. That way we're guaranteed this is going to alternate, because we'll have a positive times either a plus or a minus depending on the term. So what it says from here is that the alternating series, both the one that starts with negatives and the ones that starts with positive, but then toggles back and forth between plus or minus, will both converge. So interestingly enough, like this is different than what we've seen many times. This is only for convergence. And that can take a little bit to get there, but this only works if you deal with convergence. So the only thing you can do with the alternating series test is prove that a series converges. So keep that in mind. So both will converge if two things are true. First, if the terms' magnitudes, since that's really what a sub n is, you're dropping the plus or minus sign, if those terms' magnitudes go to 0. So first and foremost, the terms have to decrease at least as they go to infinity all the way down to 0. So that's the first requirement. Our terms have to get smaller. So it seems like a fair thing. It doesn't necessarily surprise because other things require it too. But now in addition, like technically I think I spoiled, I said something about decreasing. That's not necessarily true from step A, but it is true from step B. It says that the n+1 term has to be smaller than the nth term for all n larger than some integer. And I've called that integer capital N here just for simplicity and so that it's similar to the one that we have. But basically this is saying that your terms have to start uniformly decreasing after a certain point. So for us, we're just saying it's at the integer n. Doesn't matter if it doesn't start decreasing till term 1, term 42, term 76,848. Not sure how that would happen, but UBU. But those are the two things that are required. So terms go to 0. Actually, there's nothing really to say here. Terms go to 0. And then second, that the terms decrease after a certain point, so that they uniformly decrease. And now, having said that, it talks about these separate things. Considering these two properties, the one that I think is the most relevant to bring up here is number 1. I want to note that if number 1 fails, let's see if I do this right. Oops, why did I say number? Geez, let's just do that. If capital I fails. So if you're looking at this and the first property fails on your series, then that's going to mean that your series diverges. And I'll dig deeper into this fact in a little bit. Like, spoiler alert, one of our examples, or one of the examples I came up with, features an opportunity to kind of illustrate and talk about why it is that this would be true. But specifically, the series will diverge not by alternating series, but by the nth term test. And if you think about that, and again, hopefully the nth term test isn't too far in the past for you to get fooled by, or to have forgotten. Hopefully you're not forgetting it all. But basically the reason would be, if this isn't true, then of course your series doesn't have terms going to 0, which means you're going to be adding something that has, a size over and over again, which would take it to infinity in some way. But again, maybe I'm getting ahead of myself. I just want to be as comprehensive as possible. We'll look at what that reason is and kind of give you some explanation for it in just a little bit. That is, though, the alternating series test, which is our only test that we're going to be dealing with today. Having said that, let's dig in and start to look at the things that we would normally. Let's try to prove or verify whether a series converges or diverges, or show, demonstrate. Demonstrate's the verb I want. That's the verb I want. Let's demonstrate that a series converges or diverges. And of course, the odds are I've chosen these problems to support the alternating series test, so that's what we're going to look at. So we'll start right here. We've got the alternating series test. Let me point out that the alternating series test requires 2 properties. And you know what? I can be that guy. I'm going to go ahead and steal those 2 properties. So I'm going to make them a little smaller. There's where we are. I'll put it in pink up there. So that's what we're trying to show. So I'm going to start by verifying or checking both properties. So let's start with property 1. The question is, what is the limit as n goes to infinity of a sub n? Well, first of all, I probably should have started up here by saying it this way. Based on what we see, a sub n is going to have to be equal to 42 over n plus 1. Notice that it extricates it from the toggle. We've got the toggle sitting right there. But we want to look at the magnitude of the terms itself. This would be the magnitude of those terms. It's how big each one is. That's the same thing as, of course, looking at a sub n. So having said that, we want to find this limit to see if the terms are going to 0. In this case, that means we're evaluating the limit as n goes to infinity of 42 over n plus 1. Now, if we evaluate this, that's going to be 42 over infinity, which is 0. So the first property of the alternating series test is good. We're good to go. We're in good shape. We've got one property down. Everything looks nice. So our second property is all that's left. You can see that the alternating series test is pretty clean. The second property is to check the adjacent terms. We want to see if a sub n plus 1 is less than or equal to a sub n. And yes, it's only for all n greater than or equal to a certain number, or greater than a certain number, but for now we'll just kind of set it up and see if it's true. And then we can deal with that other stuff later. So in here, that would lead us to 42 over n plus 1 being less than or equal to 42 over n plus 1. Question is that true? Well, that's the same thing as saying 42 over n plus 2 is less than or equal to 42 over n plus 1. Notice that those two expressions are exactly the same, but the bigger denominator is on the left one. And if we have a bigger denominator, that makes this statement true. So that means that this is also true. So we now have the second property required by the alternating series test holding. So what we've just shown are that both necessary conditions are true. And of course, it shouldn't have gone without saying, but the truth was this is clearly an alternating series because -1 to the end is clearly a toggle, so it's clearly switching the signs back and forth. That means we've done enough. We can now say all that we need to. Therefore, our series, which again, as I've done this whole unit, I will faithfully write out in its complete and totality. This thing is going to converge. And it's going to converge. I should say it correctly. The series converges by the alternating series test. Which again, it can't diverge by the alternating series test. But it can converge if those two properties are met. And we found that those two properties are indeed true for the series in question. So voila, there is the conclusion we were looking for. You know, I'm just not going to box them anymore. Like, I just don't feel like I don't feel like a successful person when I try to box things. So I'll just stop right there. But there's your work. We've just used the alternating series test to prove this series converges. Having said that, of course, we want to look at other possibilities. You know, there could be some other tricks out there. There could be some pathological cases. Those often show up in math. So we're once again going to try to analyze the behavior of a series. And as we look at this second example, you'll notice the presence of a toggle right here. As soon as you see that toggle, that tells you that the alternating series test is probably a candidate for us to look at. So just like we did before, let's pull in the statement of the alternating series test and just kind of have it on hand so we can be ready to go. Now, just like we did before, I can put it in pink this time. Because we've got the toggle here, we want to isolate the magnitude of the terms. That magnitude will be a sub n equals n squared plus 3 divided by n squared. And by the way, you might have some bells going off in your head right now based on stuff we talked about. But again, if you haven't, that's cool too. No rush to get there. We do, though, want to start to attack this problem. So let's check the two necessary conditions to use the alternating series test, since clearly the signs are alternating, judging by the presence of that toggle. So property 1 says we need to check and make sure that the limit as n goes to infinity of a sub n is equal to 0. That means we're going to evaluate the limit as n goes to infinity of n squared plus 3 over n squared. So having said that, when we go to evaluate this, you could use L'Hopital's rule twice. You could do a bunch of different things. But no matter how you get there, you're going to find that this limit is equal to 1. And 1's a great number. In fact, if you haven't lost, you've won. But at the same time, the problem with 1 is that it's not what we were looking for. It says that you need to have that limit of the magnitude of the terms go to 0. And unfortunately, 1 and 0 are different things. So what that tells us right now is that this series is actually going to diverge. Like, in fact, we've just proven that the alternating series test is woefully inadequate to take care of this thing. We're actually done. So I'll say right now, just so we have it, we can go ahead and make our conclusion. We can then say that therefore this series, which, because I'm suddenly a lazy person, I'm going to bring down here. We can say that this series actually diverges. Now keep in mind though, the reason this series diverges is not the alternating series test, because we can't even apply the alternating series test. That series test only works if your limit goes to 0. So unfortunately what we have to say is that this diverges by the nth term test. Sometimes called the nth term test for divergence, because that's all it proves. And in fact, this is a nice conclusion. Having said that, though, I do want to think for a moment and kind of demonstrate why it is that this is telling us that we can't conclude that this is going to converge. Like, this might not necessarily jump out at you because of the presence of that plus or minus 1. Well, basically, let's think for a second. Let me draw a brain. Okay, it's not my finest brain ever. There's my brain. Inside this brain, I want you to think about the sum as n equals 1 to infinity of -1 to the n times this thing a sub n. So that sum's going to start with something. So if we start at n equals 1, by the way, just so that we stay accurate, it's going to be 4, like I'm just plugging 1 in up here just for accuracy's sake. It'll be negative 4 plus, if we put in 2, it'll be 7 over 4. And then, of course, there'll be more terms. But then keep in mind, now, the whole reason we did this was because what we were showing was that this limit tells us that the magnitude of these terms is going to get closer and closer to 1 the further we go on. They'll effectively be 1 if we go on forever. That means that at a certain point, our series will become plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus ... And what we'll keep doing is we'll keep changing our sum's value. We'll keep oscillating, hey, there's the word. We'll oscillate between two different sums, the plus 1 version and the minus 1 version. And unfortunately what that tells us is even though those numbers are fairly close to one another, like they're not differing by more than like 1, the problem is we're going to keep oscillating between two discrete values. Discrete meaning two very different values. And that means that we can't say it's approaching any one thing. It's just literally oscillating. And because of that, this series diverges. If you don't believe me, let's go ask the Desmos. There's Google. Let's go see what Desmos has to say. I need to use I need to do Desmost. Okay, n squared plus 3 over n squared. N squared plus 3 over n squared. Negative 1 to the n. Okay, so the question is, do we see this going to any one particular place? And the truth is I haven't done this demo before on Desmos, so I'm hoping it's going to be useful, but we'll see what happens. So take a look at our sum. There's our sum that we're looking at. Oh, you know what? I can actually see it. Can you see it doing that? 2.46, 3.46, 2.46, 3.46, 32, 32, 32, 32, 32, 32, 32, 32. So you can see what's happening here is it just kind of keeps bouncing between those numbers. Yeah, they're changing a little bit as we go, but that change is just kind of going dun, 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 dun. It's basically toggling almost. And of course, we're only going to 100. So basically, just imagine if we went on forever, it'd just be toggling a more and more precise version. Oh, look at that. Oh, I didn't know what was going to happen, but look at that thing. There's the sum graphed out. I don't know if you can see it, what I can see. But look at that. It's just literally bouncing between those two different things. Like this is actually, truthfully, I feel really clever and smart right now because this worked really, really nicely. You can see that this is alternating. And yeah, they're sort of moving towards each other a little bit, but unfortunately we're not going to get anywhere during that time. It's just going to keep bouncing back and forth between those two values. I think it was like negative 2 point, yep, there it is. Negative 2.467, negative 3.468. Like there's where we're at. That's the nature of what we're looking at. So if you were curious, there's part of your reason, like in fact that this would diverge. Just keep in mind, I'd say the bigger mistake here is not that people forget that this diverges, or maybe hopefully not even that they don't understand why, but specifically that it diverges by the nth term test, not by alternating series test. Having said that, even though this is a pretty small bit of it, and it's pretty early in the lesson, I do want to give you an opportunity to just kind of practice with this a little bit. I want you to get those mechanics down and kind of look at a comprehensive slate. So if you're into doing kind of some intermediate practice and kind of pacing yourself, please do take a look at the first try it. Connects right here, and it'll give you a chance to get a feel for the alternating series test and some of the requirements that are in there. So again, I don't think this one's particularly challenging compared to some of the other ones that have been out there, but please do take a look if you'd like to. And while you do that, I'm going to take a short little break, and then I'll be right back to talk more about the sums of alternating series, which should be something very interesting. Okay, having given you a little bit of time, taking a little bit of break to myself. First time I didn't take that break and find a bunch of news that left me feeling awful inside and rocked to my core. So that's a good thing. But having said that, I do want to move on from here. We've seen the alternating series test, a pretty simple one to apply. In fact, we see that there's some very rigid and very straightforward conditions to kind of check to make sure you can apply it. We want to we want to begin to talk about the sum of an alternating series in situations where we can't actually find it or we don't necessarily know how to get to it just yet. Oops, need to press that button. Okay, so the question guide here is not one that you would naturally come up with yourself, so consider this kind of a rhetorical question. The question is, can we approximate the actual sum of an alternating series? Like, when is it that we can do this really well? Obviously, if the series is alternating in geometric, we actually have a formula in which to find it. It's the a sub 1 over 1 minus r. But if the series isn't geometric, the question might be, is it possible for us to do this? And what sort of information can we use to get there? So as it says up here, with this theorem, there is indeed a way that you can get some information about the sum, and in fact you can bound the sum, meaning that you can find a small window in which the actual sum must lie. We're not going to be able to find the sum itself using this process, although some of these series I do happen to know how to get there, and you will eventually as well. But for this, for sure, there is a way that we can at least, hone in on the range in which the actual sum is going to fall. So what the theorem says is, for a convergent alternating series, the magnitude of the difference between the actual sum s and the nth partial sum s sub n is less than or equal to the first omitted term. And in fact, it should say the magnitude of the first omitted term. So I actually caught a couple mistakes on proofs and stuff in here. The magnitude. I can't spell magnitude. Magnitude of the. Had to squeeze the in there, but that's okay. It can survive. So is less than or equal to the sum of the magnitude of the first omitted term. Now, when you hear that, you naturally probably go, what? Like, what? It's a lot of stuff. So let's do this. Let's offer a quick little translation. Not a too long didn't read, because as I mentioned, I think before in one of these, like, I'm not really fond of that whole strategy. Like, oh, you're not important enough for me to pay attention to. Let me give you a cheap out. No, that's not what this is. This is us translating it so we can understand it better. So here's what we're talking about. So they're talking about something called the error. Like, it's not coming up in the words here. It doesn't say the word error at all in that theorem. But they're really talking about the error. So I'm just going to call it what it is. The error. The error is going to be called, and I want to make sure I use the terminology, the symbols and everything correctly here. Our error we're going to call r sub n. Technically, the reason there's an r there, not an e, is because r stands for remainder. Some people like to call this a remainder instead. So we'll go that way. But there's this thing that's an error. It's called r sub n, and it's equal to the magnitude of the difference between the actual sum of the series and the nth partial sum. So a couple things to point out here. We've got this guy. Oh, wait, what if, oh, geez, I just had an idea. Had an idea. Let's see what happens. So we're going to go that way. Oh, is it not going to let me? Oh, are you kidding me? Oops. It doesn't want to help. I was going to say, let me use some color here. This might actually work nicely. So we're going to do this. Sorry, I'm going to get this thing right here. Trying to coordinate all this color at once isn't easy. There we go. You get to see the realism of it all. Okay, second, we've got this partial sum, s sub n. So let's go ahead and paste this in right there. It keeps wanting to put it at the bottom of the screen. I'm not sure why. Okay, so there we go. So what we're talking about here is we're trying to find a way to cap or narrow in on the range between, or the difference between, the actual sum, if we were able to add up all infinity terms, and the nth partial sum, wherever we decide to stop. And it says in here that this is less than or equal to, so I mean that's not anything too fancy, I can put that in there, is less than or equal to, and then it says here, this is the part that might be easy to miss, the magnitude of the first omitted term. So the magnitude of the first omitted term is going to be the absolute value, so that way sign doesn't matter, of a sub n plus 1. So this is what's often called the max error. Later on in the course, like theoretically, we'll call this the geometric series error bound, or the geometric error bound. But the important thing is to talk about all of these pieces here. We've got the actual sum in purple. We've got the nth partial sum, which is in that kind of plum color. And we're saying that the difference between them is maximized. Like the largest that error, that difference between the actual and the approximate could be, is actually the n plus 1 term. That is the first omitted, meaning that it's the first one that's not included in the partial sum. So it's a little strange. But let me try this one more way. I'm looking at ways that I've done this in the past to try to see if I can share some of them. So something we could look at. 1 minus 1/2 plus 1/4. I'll go back to a classic favorite, alternating series. Okay, so here is an alternating series, and of course it goes on. Actually, I'll go a few more terms. There. It goes on for a while. So what we're saying is, if we decided to, and I'll use the color here, if we wanted to try to approximate the error itself, we could look at a particular partial sum. In this case, for instance, I might look at the partial sum s sub 4. So far, so good? Hopefully okay. So from there, what this says is that the difference between the actual sum, like if we added up all of the terms forever, like s or s sub infinity, if we wanted to call it that, the difference between those is bounded by this. That guy, is that what I called it before? Well, a couple things to point out. First of all, this whole area would be what we'd call r sub 4. It's the remainder, or the sum of the remaining terms, or the error in our partial sum, however you want to think about it. And this guy, then, would be the bound for the error. So basically 1/16 is the largest we could possibly be. Like, we know that the actual sum is within 1/16 of whatever this is equal to. Now, all of this is a little bit weird, especially here because I just showed you a geometric series, and that's not even necessary because we know how geometric series work and we know their sums. It'll be more relevant in just a second. So first I'm going to just kind of expose you to the proof a little bit, then I'll do an example to hopefully kind of hammer this home and try to get it close by, because of course I can't answer questions when doing things this way. So your proof here, this is a complicated proof, and I'll tell you what, I've read over it. I read over it last night a couple times. I read over a few times today, just trying to get my mind around it so that I could just basically narrate through the proof as best as possible. Again, this is not something that would pop up on any sort of assessment, I don't think, at least not in the kind of courses that I teach. But it's definitely something that's worth investigating a little bit, just to kind of see it work through and to kind of get the idea of why it works and why it relies on an alternating series test, like properties that we've seen before. So in here, first of all, they define r sub n. What is showing up? Something is showing up on my bottom thing. I think it's a Steam notification, whatever. Basically, we start by identifying the remainder or error term as s minus s sub n. Then from there, as we said, s is the entire series sum, which is from 1 to infinity. And then s sub n is just the sum of the first capital N terms. So it goes up to whatever that term n would be. Well, if we subtract those two things, gosh, I don't know why that thing's going so crazy down there. Maybe you can't even see it. So from here, what we do is we look at that difference, and basically by removing the first n terms, that leaves us with the n plus 1 term, and the n plus 2 term, and the n plus 3 term. So it leaves us all those guys. And what I do is I then factor out a GCF of the toggle. And what that leaves me with is a series that's still alternating. You can probably see it's still alternating. It goes plus, minus, etc. But the difference here is we now start with a sub n plus 1, which, by the way, according to what we were looking for, is what's called the first omitted term. So having said that, when we look at that remainder, we can now describe that remainder as being equal to this thing. But the thing about this remainder is, because this is an alternating an alternating series, we know that the term's magnitudes have to decrease. So here, that means a sub n plus 1's magnitude is smaller than a sub n plus 1's, and a sub n plus 2's magnitude is bigger than a sub n plus 3. So what they do is they then take pairs, and you can factor out a GCF of a negative 1, so that you get it as a sub n plus 2 minus the next term, and then minus a sub n plus 4 minus the next term, then minus a sub n plus 6 minus the next term. And basically what you do is you're subtracting a bunch of stuff. But because those things, this is a convergent alternating series, the terms have to be getting smaller, which means this one's bigger than the second one, so the entire difference in there is positive, because we're taking a bigger thing minus a smaller thing, and that means we're subtracting something positive. Over here it's the same thing, we're subtracting something positive. Over and over again we're subtracting something positive. And because, what happened? Because we're subtracting something positive, that means that this value is smaller. This entire thing is less than or equal to a sub n plus 1, which, because we've pulled out the toggle, is really the same thing as the absolute value of that term. So having said all that, that means that our error, which is right, that's a terrible or circle, but our error is equal to that n plus 1 term, also known as the first omitted term, minus a bunch of positive things, which, as it says right here, is less than or equal to a sub n plus 1. Having said that then, we've just shown that the difference between the approximate sum coming from the partial sum and the actual one is less than or equal to the next partial sum, or the next omitted term. So there it is. We've actually just proven this property of alternating series. So again, I realize that's probably not the most illuminating thing in the world, but again, I practiced a ton for that. Probably should have invested more time on the explanation of just the error bound thing on the previous one, but there's where we are. So now, having said that, I promised we'd look at how to actually do this. So let's do precisely that. I want to show you what it looks like to do one of these sorts of analysis works to talk about the sum. So first and foremost, as we look at this thing, we want to use 5 terms to approximate this series. And 5 terms seems aggressive, so you know what? We're not going to. We're going to use 3 terms. I think 3 terms will be just as good, and it'll just take us less time and be a little cleaner. Let's see, I'm trying to think. Should I do more? You know what? I'm going to do one more thing. This is me making these problems. Why don't I change it again? I'm going to make that 42. That way we'll have nice numbers. I just want to make sure that the numbers are clean, everything's integer based, so that way there's nothing obscuring the actual structure of what we're doing here. You'll get more challenging problems, I'm sure, some other time. So now, having said that, we want to talk about this rule here, basically. And it's basically this thing. So let me go grab this guy. Let's go throw this just up in the corner. Let's go hide it in the corner. Like that mother in the movie Hereditary. Sorry, spoilers for multiple-year-old scary movie. So anyway, there's our stuff. There's our thing that we're trying to do. So in this case, we're using 3 terms. So I'm going to point out that if we were to write this out formally, we'd say R sub 3 is equal to the difference between the sum, which I'm going to call S, and the third partial sum, which is using 3 terms. So that's, again, the reason why we have S sub 3. And that, according to the information in the statement that we just proved, is going to be less than or equal to the absolute value of the next term. So for this case, I'm going to put the absolute value of A sub 4, because that's specifically one term after the 3 that we're using in the partial sum. So far, so good? Cool. Okay, from here we've got a couple things that we need to do. The first thing I want to focus my attention on, I'm going to try to change the color of things. It just doesn't want to cooperate with me. The first thing I want to do is I want to figure out what this sum's equal to, this partial sum is equal to. So the reason I bring that up is that I want to figure out what it is, because the partial sum is going to play a huge part in how accurate our sum is. The more terms we include in the partial sum, the more accurate we'll get. So first of all, S sub 3 is going to be the sum of the first 3 terms in here. Now looking at this expression, we're starting at 1. Our toggle is -1 to the n plus 1. So the first value will be -1 to the 1 plus 1, which is -1 squared, or positive 1. The reason I bring that up is now that I've seen that, I know my first term will be positive, my second term will be negative, and my third term will be positive. It's just a way to get rid of that sign issue that might otherwise kind of mess us up. So based on this information, we're starting positive. That will be 42 over 1. The next one will be 42 over 2. Then it will be 42 over 3. If I combine these things together, I get 42 minus 21 plus 14. That's equal to 35. So that means the sum of the first 3 terms is going to be equal to 35. So that's our partial sum. Next, I need to figure out what the 4th term is going to be. So from here, I'm going to figure out, no, it doesn't want to do that either, whatever. I want to figure out the magnitude of the 4th term, because that's going to cap our error. It's going to say this is as big as the error can get. This is as far away as possible. So in our case, the absolute value of A sub 4 is going to be the absolute value of -1 to the n plus 1, and then times 42 over 4. Aha, so not a perfect number. So in this case, the absolute value means that whether positive or negative doesn't matter. It's still going to be positive. And then the value here will be 21 over 2. So far, so good. So we've got our term. What we then can say, based on all this information, is we now have everything we need. That remainder, or the error, is going to be the difference, the magnitude of the difference, of S and S sub 3, which we said was 35. And that's going to be less than or equal to 21 over 2. So having done all that, we've completed a statement, but would you really say that we've approximated the series sum? Because I wouldn't. So basically what we want to do to get the actual approximation is we want to figure out what in the heck's going on with s. Like what values of s are possible given these restrictions, given that we know the error or the difference from that partial sum can only be 21 over 2 big. Well, the way we do that is we just solve this inequality. We're just going to actually solve this. So in this case, there's lots of ways to get there. This is a conjunction, so there's a couple different ways to get there, however you do it. I'm going to do it the way I was taught in middle school, since this one is a conjunction. That'll give us the inequality, the combined inequality. Let's see, this will be between, the sum will be between negative 21 over 2 and 21 over 2. Again, if you wanted to do it as two separate inequalities, bring them together at the end, be my guest. Be my guest, be my guest. But anyway, from here, I then want to add 35 to all three sections. Of course, I'll point out to you that 35 is the same thing as 70 over 2. So I'm going to add 70 over 2 to both of these things. When I do, that gives me an inequality with s at its center. We know the value of s is somewhere between 70 over 2 plus 21 over 2, which is going to be 91 over 2. And then on the next one, we'll have 49 over 2. Pretty sure that's, let's see, 69 minus 2, yep. And so what we've just done is we've found a small window in which the actual sum is going to fall. And we now know that the actual sum is somewhere between 24.5 and, what is that, 45.5. So we know that the actual sum is somewhere in there. Now the question might be, is that actually true? How could we actually check if that turned out to be true? Well, I don't know. We could add up a whole bunch of terms. We could also go to something cool like Wolfram Alpha. Let's see what that sum actually is. Sum from 1 to infinity. What was our series before? Negative 1 to the n plus 1. Oh, we got to put that in parentheses also. And it was times 42 over n. Let's see what this series sum is equal to. And then, of course, check to see if that falls in there. It says it's equal to 42 log 2. Ooh, there's a 42 in, oh yeah, of course there is. I knew that sum. Yeah, whatever. It says the approximation of the sum is 29.112. Does 29.112 fall in between? So we're being told 29.112 dot dot dot. And is that less than or equal to 45.5 and greater than 24.5? Heck yes it is. It says that we've done everything correctly. So again, there it was using it in there. I'd say that this is one of those types of problems that kind of gets you at the beginning. It feels a little uncomfortable as you kind of wrap your mind around it. Again, it might even be worth looking at that proof again later if you want to, or kind of thinking about what it's saying. But the important thing is that you can set all this stuff up, that you can find the two required parts, the partial sum and then that term, the first omitted term, and then that you can solve an absolute value inequality, which is something that I think you've been doing for quite a while. So mechanically it's not that difficult, but conceptually it takes a little bit to wrap your mind around, and I completely get that. So, I mean, I get that. What more can I say? Well, having said that, there is one other way we could ask a question that's similar to this one. And unfortunately, I've chosen a problem that requires us to use a calculator, whereas most of this unit does not require a calculator. So bear with me, we will have to pull back in Desmos in just a second. Having said that, the other question we want to ask isn't what is a good approximation for the sum, or what's a window that the sum falls into. The other question is, well, how many terms would you need to get to a certain accuracy level? Because maybe you're looking at an alternating sum or an alternating series, and it's not practical for you to figure out the actual sum, or you don't have Wolfram Alpha handy because, I don't know, your data is being throttled or capped or something. Like, who knows what the cause might be. And the question would be, well, how many terms would it take to get there? Like, how many terms can I get to a certain level of accuracy? So the question here is asking how many would we need to estimate the actual sum of this series to within 1/142nd of the answer. Notice that this isn't telling us what the answer is. We aren't finding the actual sum. We're just trying to see how many terms we need to include so that our approximation was accurate enough. That's all we're shooting for. So having said that, let me make an adjustment here. I just want to make sure that we do this correctly. So let's think about first what the requirements are for this. So what we've been doing is we've been saying that the actual sum, I'll even write the word actual in there, the actual sum minus the partial sum is going to be less than or equal to the n plus 1 terms magnitude. So far so good? Cool. You can see how much less comfortable I am with trying to talk through this stuff. This is one of my least favorite topics, honestly, trying to make sure that I stay organized here, because I can always solve the problems, not necessarily in a way that communicates my understanding effectively to you. So having said that, where we're going to begin is we're going to, of course, be focusing our attention right here. We actually don't care about the partial sum itself. We just want to figure out when does the term hit that stuff that we need. And okay, I've reached the point where I'm starting to get frustrated. I don't even know why Steam pops up every single day. Haven't played it in a while, especially on this computer. Okay, so from here, where are we going to begin? Well, let's just go talk about the terms themselves. So the absolute value of all the terms of this series will have value, or magnitude, 4 over n cubed plus 10. So that should make sense at least. Like all the terms follow that pattern. That's just what we mean by a series. So having said that, the question we want to answer first, and at least this is the way I usually find it, is, well, okay, when does a term, at what value of n does a term hit that value 1/142nd? To answer that question, as I said, I didn't design this problem perfectly, so we're going to go ask Desmos really fast. So let's see here. We want to figure out when, 4 over n cubed plus 10. I think I did that right. Yes. We want to figure out when that's there. Sorry, I put that. Let's go y equals. So let's pull back a little. Oh, there's our series. That's fun. We want to see when it equals 1 over 1/42nd. So looking in here, let's see. Oh, it's just too hard for me to see. Let's make this y-axis. Let's go from 0 to 0.5. Nope, still not small. 0.1, 0.05. Too small. Aha! I don't know if you can see it. I was just trying to get it so I'd see those two things crossing. So there it is. It says that those two things cross or have the same value when n is 8.233. So these two things are equal to one another at n equals 8.233. So good news is we've sort of solved the equation. The bad news is there is no 8.233 term. Right? Because we're only talking about terms, so they're discrete. They're valued only at positive integer values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The problem is this is suggesting that the term we want is somewhere between 8 and 9. So here's the thing. All we've really done so far, or based on that information, is we've kind of found another kind of inequality. What we've shown is that there are two terms there are two terms whose magnitude is bounding 1 over 1/42nd. Or at least we can relate now two terms to 1 over 1/42nd. First of all, since n equals 8.233 is going to be the term that makes it a equal 1 over 1/42nd, an imaginary term, but play along for the moment, what we can say for sure is if we consider that's proximity to 1 over 142, we've just shown that the magnitude of the ninth term is going to be less than 1 over 142, because of course if n equals 8.233 is the one that makes it equal, n equals 9 is going to be a bigger denominator, which will make it smaller than 1 over 1/42nd. Likewise, we know that that's all going to be smaller than the eighth term, which means the eighth term isn't quite big enough for us to bound appropriately the way we want to. And having said that, what that means is that if we want to set this thing up properly, what we've got to do is we've got to say that the actual sum we're trying to, approximate accuracy towards is going to be s minus s sub 8. And the reason I'm choosing 8 is because we saw that 9 is smaller, but 8 isn't. So that means that what we really have here is that our error bound, or the value that's going to be smaller, is going to be a sub 9. And as soon as you have a sub 9 in there as the first term that's small enough, then you're able to kind of sneak back in and put in the eighth there and say, okay, so the number of terms we want so that our partial sum is within 1/42nd of the actual sum, the requirement for that would be that we have a partial sum with 8 terms, which means that we need 8 terms. We need 8 terms in our partial sum. I'll even write this all out. Partial sum for that accuracy. I'll actually just say for accuracy of 1/142. So there is our answer. So now, if you're someone like me who has always been kind of like bugged out trying to explain this, it's something I can do. It's not something easy for me to explain. I definitely don't feel like I'm doing a great job of explaining this perfectly. Something that's helpful is to notice the approach that I had. I solve the equation, I figure out how it bounds, and of course, since the terms are decreasing, the larger one's going to always find here. And then the number of terms is going to be the term that's larger than it. So there's some easy ways to make this a solvable problem, but I think if you just kind of play with it a little bit and start to look at things, you'll actually be able to make this work out just the same too. Having said that, I think this would be a great time to give you a chance to actually do that playing, since watching a video this way is sort of different than a traditional classroom setting would be. So there's a little bit more flexibility. There's definitely some flexibility here. So having said that, I've got a second triad here that's talking about the alternating series sums. In this case, the first problem asks you to approximate it inside a closed interval in the way that we started things off with, and you've got strategies for that. And then the second one asks you to determine how many terms it takes to get to a certain accuracy level. And I think that second one is a really good problem to cement this concept and really kind of grapple with now. I think it'll pay off later in further work that you might be doing with this concept. So just as before, I'll give you a few minutes break, or I'll take a break. Actually, at this point, I keep saying I'll take a break. I am taking a break. The video won't stop for very long. So if you want to do this, try it right now. Please do pause the video and take a look at it. But I will physically take a break and then return to wrap up the final section of this lesson. Okay, I've taken my short break. I'm ready to get back to business. Hopefully you've gotten good information and good practice out of the try and gotten a chance to especially kind of get used to that thinking process, particularly for questions like number 2. So from here, where we're going to move on to is a last theorem and some related properties that will come along. There is an extensive proof in here, but this isn't going to be one that I'm going to spend much time on. I'll just do a quick little overview and then move forward, because I want to wrap this up and let you focus on just kind of the vocabulary, as well as the fact that you can see these things really, really quickly. So where I want to start is I want to talk about a particular series that's kind of strange. I want to talk about the series cosine of n over n squared. Now this is an easy series for you to write out the values of. This is the same thing as cosine of 1 over 1 plus cosine of 2 over 4 plus cosine of 3 over 9 plus cosine of 4 over 16. And at first, unfortunately, if you look at this series, it might seem like it's misplaced for the lesson today, because it looks like all those terms are positive. But here's the thing. You certainly are not positive about that fact. You can't be positive about that because it's not true. Remember that as far as quadrants go, the values of cosine are positive in quadrant 1, negative in quadrant 2, negative in quadrant 3, and positive in quadrant 4. And again, this is specific to cosine. So from here, if we know that, based on this information, since this is pi over 2, which is about 1.57, this is 3 pi over 2, which is about 4.71, and of course pi is 3.14. What we see is cosine of 1 is actually positive, cosine of 2 is negative, cosine of 3 is negative, cosine of 4 I think is negative also. So unfortunately what we're seeing is that this pattern has positive and negative terms, but it's not alternating. So unfortunately that means that theoretically we have nothing we could use to talk about this particular series. It's just outside of our realm of control. But the truth is, not so fast. We can actually add a simple theorem that allows us to conclude that this thing actually has, we can get a better handle on this series at least. So that statement is right here. Just a second, that seemed weird. So the theorem itself says the following. It says, if the series with the same terms but all positive converges, then the series a sub n also converges. So this is a little strange, but basically it says if we ignore the signs completely and just make all the terms positive, and the series that we look at converges, then the other series that has the signs changing will also converge too. So now as far as this one, this is more of a, this isn't a theorem that has a name where we're going to memorize it, but I do want to think about this series for a second and kind of talk about it. So let's try to follow the statement of the theorem a little bit with the series that we were looking at before. So let's take a look at the absolute value of cosine of n over n squared, or the sums of the terms. Geez. It's hard to say these things. There's so many things. Sequence and series, they should have really had different letters on that. Same thing with terms. Like, let's look at the series whose terms are all positive, but otherwise the same. So up here, if that's true, like basically what I want to point out is, of course, if you're writing out what this is equal to, the n squared is already positive. So instead we can really just think about it as the absolute value of cosine of n over n squared. And the reason I start this off is because there's something that's kind of neat about cosine of n. Cosine of n is between -1 and 1, because cosine is nicely bounded that way. -1 is the smallest value cosine ever gets, that occurs at pi, and 1 is the biggest it ever gets, that would occur at 0, or 2 pi, 4 pi, 6 pi, all those different things. So having said that, that means that the absolute value of cosine of n is less than or equal to 1, because that way we're in the entire region. And the reason that's true is the reason that's relevant, the reason I would even bring that up, is the fact that then we could say that the absolute value of cosine of n divided by n squared is less than or equal to 1 over n squared. So having said that, what we've just shown is that we can now show, or what we've just shown is that there's a term-by-term comparison that's valid here. And they're both positive, so this works out really nicely. So according to this, we can then say that the sum of cosine of n over n squared from n equals 1 to infinity, that sum is less than or equal to the sum of 1 over n squared from 1 to infinity, and that is a convergent p-series. You can see that this is easier to talk about than it is to write, but I'm trying to be faithful to describing everything on the screen. So it's a convergent p-series, and therefore, by direct comparison, what we've just shown is that the series here with the absolute value of cosine of n over n squared is going to converge. And the reason that's relevant is as soon as we know that, according to our theorem up here, that means that our series, which was from 1 to infinity, of the terms that have some negative signs mixed in, we are able to say that this series converges also. And then as far as the why, it's by that theorem. But for the moment, it was more just to illustrate that this absolute value thing really helped us quite a bit. It opened up some pathways that we wouldn't have been able to access with the tools that we had already, which were strictly alternating series that toggle back and forth in sign. So having said that, the moral of the story isn't that you need to know this particular example. It's not some canonical special example. It's more the idea that analyzing the behavior of the absolute value of a series tells us some information about the alternating version, or the one that has some signs that are changing. So having said that, what I want to bring up is this new concept. It has its own little definition here. Basically, there are two different types of alternating series. Those two alternating series types are the following. So if you've got a convergent alternating series, the series is either absolutely convergent, and that occurs if the absolute value of the series converges, or the series is what's called conditionally convergent, in which case the alternating series converges, which of course it does, we said that was a requirement, but the absolute value does not. And this can be a little tricky when you start to look at these the first time, so let me just first give you an example of each of these things so you can kind of see what I mean. So for instance, here is a series, sorry, I guess I'm using the wrong color, green, but here is a convergent alternating series in which the absolute value converges, in which case we would describe this alternating series as being absolutely convergent. The reason is, when we look at this particular series, you notice that the absolute value version is going to be the convergent p-series. So that, which is equal to the absolute value of, -1 to the n over n squared, that converges by p-series. So because the absolute value converges, that means that this series is what's called absolutely convergent. Likewise, we can talk about the series for conditionally in the same kind of manner. So let's look at the series n equals 1 to infinity, and let's do negative 1 to the n over n. So think for a moment about what we know. Well, this is definitely a convergent series, but if we take its absolute value would be this, which is known as the harmonic series, and that harmonic series diverges. So that means that in this case, although the alternating version converges, the absolute value version diverges. And that means that there are only certain conditions under which that series converges. It requires and needs that alternating sign, that negative or that toggle to be there, otherwise it's going to be a divergent series. So it's not going to converge absolutely, where whether positive or alternating or signs changing, it's convergent. In the second case, if it's possible for one of them to not converge, the positive one to not converge, then we call it conditionally convergent. Now, having talked about this, we talked about that property a second ago, so there's some powerful stuff here. Basically, there's some cool ways that you can actually demonstrate that an alternating series will converge. But as I mentioned, trying to prove that property that was there a second ago, and really this should go before what I just was showing you, but I guess it was just to make sure that we got into the vocabulary. This proof uses direct comparison to convey and convince you that this property holds and is true. So in other words, this idea of absolute convergence implying convergence for the alternating one. If you're interested in looking at it, I encourage you to go to that link. That's where I found and kind of a good outline to help me script out my proof here. I think it's very similar to the one that they have, so all credit to them. So feel free to take a look, but again, this isn't my purpose. I just want to demonstrate the alternate or the absolute and conditional convergence quickly, so that way you've got that vocabulary in action already. So here's one such question. We want to classify this series as either absolutely or conditionally convergent. So in order to do that, it's not actually very difficult. In fact, I'd say it's one of the fastest things we could do. What we need to do is we need to look at the absolute value version. We need to look at the positive one. So what we're going to do is we're going to take a look at the behavior of this version of the series. So that is, of course, going to be equal to the sum from 1 to infinity of 1 over the cube root of n. Now that is a p-series. Again, you don't necessarily have to write this out, but you know that you do definitely need to write out to this point. That's a p-series with p greater than or equal to, or excuse me, less than or equal to 1. And of course, I should have said it differently, pardon me. P equals 1/3 less than or equal to 1. So what that means is that this series diverges. And as soon as we see that the absolute value version of the series diverges, that means that our series is only conditionally convergent. In fact, why am I writing it down here? I can write it right up here. Conditionally convergent. So basically the reason it's conditionally convergent is that, of course, it does converge. It's an alternating series and it passes the alternating series test with flying colors. But unfortunately, if you look at the term without the toggle, if you don't have those signs changing, then unfortunately it doesn't meet the requirements. It diverges because that's a divergent p-series. And therefore we would say that this series is only conditionally convergent. It doesn't converge in every situation, only when it's got the toggle. There, I finally said it right. Having said that, I think that's enough to go through. I think you've kind of gotten a feel for what's there. I know that last one was a pretty quick single example, but it's just kind of a vocabulary to get used to. Your process of doing this is literally just comparing and seeing what happens and then stating whether it converges or diverges. That's your entire proof to decide if something's conditionally or absolutely convergent. So I think that's probably enough, and I don't want to spend too much time working through it. I want to give you a chance to play with it and grapple with it yourselves. So here are 2 questions. I'd say these are pretty basic ones. I don't think these are particularly challenging versions. So take that for what it is. But I do want you to encourage you to work through and kind of get used to this. And of course, if in using the Google form you don't feel like you've got a full grasp of everything, then I'd say to please instead just look at the solutions to these triads and see if that can help you a little bit as well. But again, I know I moved through that last section pretty fast, but it's literally just a little bit of vocabulary, and you can tell whether or not it works or not just by ignoring the toggle and seeing whether that series converges or diverges. But having said that, I do want to call it a day right here. So as always, thank you for watching. Hopefully this has been a fairly comprehensive look at alternating series, as well as the approximation of their sum or bounding of their sum, and even the concept of convergence or conditional and absolute convergence. So having said all that, once again, thank you for watching. I hope you're safe and doing well. And again, it would be great to be telling you all these things in class and doing things like that with people around instead of just talking to a webcam. But until I can do that again, hopefully this is a good tool to support you nonetheless. So as always, thank you for watching and have a great night. Or have a great morning or afternoon. Don't let me, stop you from enjoying whatever time of day it is for you.